In this problem, we're going to illustrate the equivalence of using two different approaches, which use two different position vectors, to calculate the moment of the force F around the base of this pole O. So we know that F has a magnitude of 20 newtons, and we know that we want to calculate the moment of that force F with respect to the base of the pole, that's down at O, and we're going to do it in two ways. One way is to use a position vector from O to A, that's where the rope is tied to the top of the pole, and one is to use a position vector from O to B, which is where the man is holding the rope. And what we're going to do is show that these two approaches are indeed equivalent. So let's write an approach. So step one is to define F. And that is going to be the vector which indicates the force as a vector, which is directed along the direction of the rope. And the way we're going to do that is we're going to define a position vector, we're going to make it a unit vector, and we're going to use that unit vector to write the force vector. Second thing we're going to do is we're going to solve using a position vector from O to A. I'm going to call that RA. Third thing we're going to do is solve using a position vector from O to B, and I'm going to call that RB. And then the fourth thing we're going to do is compare and make some comments about the two approaches and make sure that they are indeed equivalent. Before we start, let me just kind of set this up while we have the image on the screen here, the two different ways that we are going to do this. So the first thing we notice is that the force vector F is directed along the rope from A to B, so we're going to have to define a vector R from A to B, and it's going to then be made into a unit vector. We're going to use that to define the force vector F. From there, we're going to do two different kinds of solutions. Let me do step 2 in blue, and that's where we write a position vector from O to A that I am going to call RA. And we're going to use that to make the moment calculation. Then in step 3, I'm going to use red to go ahead and write a vector RB. And you notice that both of those vectors touch the line of action of the force F. And what we're going to show is that they give us the same value for the moment calculated around O. So let's go to the next page and go ahead and start with step 1. Okay, step 1, define F. So the first thing we have to do is write this position vector from A to B, and one way you can do that is illustrated right here. We can start by defining the coordinates for point A and B, and we're going to do that like this. Coordinates for A are 0, 0, and 10.5. For B are 4, -3, and 1.5. And let me go back to the figure on the first page here and emphasize that the coordinate system we're using is right here. Positive x, positive y, positive z. So this is a right-handed system. And the units we're using here are in meters. So both of these things have units of meters. What that means then is that the position vector r from A to B is going to be equal to the kind of relative position vector, is what we call it, between A and B. And so to get from A to B, we've got to go 4 in the I direction. We've got to go -3 in the J direction, and we've got to go -9 in the K direction, and again, this has units of meters. So now that we've defined our position vector R from A to B, what we need to do is to make that into a unit vector. So U from A to B is equal to R from A to B, the vector, divided by the magnitude of that vector. RAB magnitude is the square root of the sum of the squares of the components. So that's going to be 4 squared plus -3 squared plus -9 squared. The whole thing square root. That turns out to be 10.3 meters. And so U from A to B then is going to be 1 divided by 10.3 times RB. So that's 4 in the I direction, -3 in the J, -9 in the K. And I should point out that since this is a unit vector, it is dimensionless. We can use that then to define the force vector F And we know the magnitude of it. It's 20 newtons. And it's going to be 20 times UAB. So this is just going to be 20 divided by 10.3 times 4I minus 3J minus 9K. And this is going to have units of newtons. So there is our force vector. Now, you can do as much or as little simplification of that in terms of the algebra, multiplying through by the 20 and dividing by the 10.3. You can do it now, or you can do it later in the solution. I'm actually going to save that algebra until a little later. All right, so let's switch to blue now, and we're going to do this part of the solution where we use the vector RA. So the first thing to do is to define RA. Let me go back to the front here, and you can see that the vector from O to A is just strictly in the z direction. So that means we're going to be able to write RA as a vector 10.5 in the k direction. It's got units of meters. So that means the moment around point O is going to be RA crossed with our vector F. So this is going to be 10.5 in the k direction crossed with 20 divided by 10.3 times 4I minus 3J minus 9K. So what I'm going to do is I'm going to collect these coefficients here out in front of the resulting equation, and this is going to turn out to be 10.5 times 20 divided by 10.3. And then if we actually do the cross product part, the k crossed with the I, the j, and the k, we end up with 4j plus 3I. And so now when I go through and do all the algebra, what I end up with is the moment around point O is going to be 61.2 in the I direction plus 81.6 in the j direction, and that has units of Newton meters. So there's the solution using the vector from O to A. Now I'm going to switch to red, and I'm going to use RB. So in this case, the vector from O to B is just the same as the coordinates for B, and so it's easy enough to write. RB turns out to be 4I minus 3J plus 1.5 in the k direction. That has units of meters. And so again, we can go through and we can calculate the moment around point O. That's going to be RB crossed with F. This is going to be 4I minus 3J plus 1.5 K crossed with 20 divided by 10.3 times 4I minus 3J minus 9K. So again, I'm going to pull out this multiplier out into the front of the equation and go through the cross product itself. So this turns out to be 20 divided by 10.3, and then we have a whole bunch of terms coming up that result from the cross product. So let me start with, let's see, the 4I crossed with 4I term. That comes out to be 0. I crossed I was 0. The 4I times, crossed with the 3J. This turns out to be minus 12K because of this minus sign right here. We can go with the 4I and the minus 9K, and that becomes a 36J. And if we go straight down the line like that, we get a term that's plus 12K plus 27I plus 6J plus 4.5I. And what you notice straight away is that the only K terms in there cancel straight away. Those two are equal and opposite. So when we simplify this, we get the moment around O turns out to be 20 over 10.3 times 31.5 in the I plus 42 in the J. This simplifies to 61.2 in the I plus 81.6 in the J, and it has units of Newton meters. So there is our moment according to the calculation with RB. So if you were playing along in step 2, you notice that that's the identical result, and so indeed these two are equivalent. But let's go ahead and make some statements here. So in step 4, we're going to compare. First thing we notice is that we get the same numerical answer. So that's good news. That means the two approaches are indeed equivalent. What we notice is that the relevant position vector in the cross product must be to the line of action of the force, not any specific point of force application. So R points to the line of action of the force F. And the last thing we might do here is that because we have this flexibility, we can choose any R that we want to, which points to the line of action of F. In this case, it seems like we ought to choose the easier one. And the thing we noticed here is that the RA analysis is easier because RA is expressed with just a single component in the K direction. Let's go back and review. So we had this problem where we were trying to figure out the moment of a force F applied through a rope, the moment around point O. And we were going to do that in two ways. We decided to do it with a position vector RA and a position vector RB. First thing we did was define the force F in terms of a magnitude times a unit vector. Then for the analysis of the RA case, we used blue and came up with one answer. For the RB case, we used red and came up with another answer, and of course those two answers were equivalent. And what we noted is that R has to point to the line of action of F, and that because we have this flexibility with how we define R, we generally like to define the R that is the easiest to work with. And in this case, that was the analysis using RA.